Hello physicists, welcome to lesson 5.4 on combination circuits. So as the title suggests, we are going to focus on combination circuits here. And what is a combination circuit? Well, let's draw a very simple combination circuit. So we'll have a resistor here, a resistor here. Those are in series, and then we'll throw in another resistor here. Okay, so we'll have a voltage, a resistance 1, resistance 2, and resistance 3, and we'll have some current going through this thing. All right, so this is a combination circuit. And why is it combination? Well, we've got a section here that's parallel, and both of these resistors that are in parallel are also in series with this resistor up here. So what we're going to do today is we're going to look at this as our first circuit, and we're going to simplify this thing so that we can figure out more information about it. We are going to take this section here where we've got our resistors in parallel, and we're going to use Kirchhoff's law for resistance. And so for parallel, we're going to use the 1 over R total is equal to the 1 over R2 plus 1 over R3. That's going to allow us to figure out the total resistance for those two resistors, and that'll allow us to simplify the circuit down to something that looks like this. Okay, so basically we've consolidated those two resistors into a single resistor. Okay, so now we could call this something like resistor 2, 3. Okay, and the resistance across there is equivalent to the resistance of the first two resistors, and we've still got resistance 1 here. And now we can see we've got these two things in series. These two resistors are in series, and so we can simplify again if we use the resistance equation for resistors in series. We're going to get this. So resistor 1 plus resistor 2, 3, which we collapse down into this single resistor. And now we're going to be able to come up with our most simplified circuit. Can't get any simpler than this. We put all of those into a single resistor, and now we can think of this as our resistance total. We're going to have a voltage total, and we're going to have some current total flowing through this. And so this is useful because once we figure out our resistance total, current total, and voltage total, we're able to work backwards. So once we've got all those things, then we can work backwards and figure out different aspects of each of these components. So if we wanted to figure out what the voltage drop across resistor 2, 3 was here, we could now do that because we know total resistance. Okay, so we'll go through some steps for being able to solve these combination circuit problems, and then we'll jump into some examples fairly quickly and just start applying this and seeing how it works in different scenarios. So first of all, to solve problems involving combination circuits, we are going to use a combination of Ohm's law. So at times we're going to be employing Ohm's law, and we're also going to be using Kirchhoff's laws for current and voltage. And importantly, Ohm's law applies to an entire circuit if the total values are used. So going back up here, we'll be able to use Ohm's law for this total circuit if we're looking for total values. So if we're looking for total current or total resistance, and we've got total voltage, then we can use Ohm's law. But Ohm's law will also apply to individual device or individual components. Let's just keep it consistent with the way that we've been talking about this individual devices. We can talk about components like resistors and things. And we can use Ohm's law when we've got individual values. So this is what I'm saying. We need to be able to work backwards. And once we've got the totals, go back and figure out those individual values. So in general, and as you get better and better at doing these, you might be able to move more quickly through these steps or find some shortcuts that you can use. But in general, the approach to solving these combination problems is the first, you're going to find the total resistance of the circuit, okay, by replacing with equivalent resistance for series and parallel branches. So you're going to go through, just like I showed you at the top there, you're going to go through and you're going to simplify these circuits by continuing to find the total resistance of parts that are in parallel and parts that are in series until you've worked your way down to a single resistance. Okay, from there you can determine the overall current flowing in the circuit using Ohm's law. And then once you've got that total current, you can work your way backwards to find the current and voltage across equivalent resistance series and branches using Ohm's law and Kirchhoff's law. And the last step is you're just going to keep repeating this as necessary until you find the current or the voltage for each individual component that you're interested in. So as a quick refresher here, we've got our resistance for series and parallel, as well as our current and voltage laws for series and parallel. So starting off with our voltage laws, okay, and hopefully everyone's very familiar with the voltage laws and why we've got voltage working additively in series and why we've got it at this equality when we're in parallel. And using both of these and Ohm's law, then we can figure out our expressions for our resistance, our total resistance in series and parallel. So again, if you need a refresher on any of that, go back and watch the last couple of videos and make sure that you're really comfortable with how we get to those resistance equations. Okay, so let's actually start putting these things into practice. We're going to jump straight into this. So our first question says, what are the values of I1, I2, and I3 in this circuit? So we're looking for I1, I2, and I3. Now, hopefully, this should be comfortable enough for you that we can go back to our plumbing analogy and say, well, if we've got a pipe that comes to a narrow point, it's actually this narrow point that is dictating the flow of the water on either side of this narrow piece. So this water on this side can only flow as fast as this narrow piece will allow, and on this side, again, it's controlled by the narrowest part of the pipe. So across all of these resistors, it's not like the current is changing when we go from this side to this side to this side of the resistors. Those things are all in action. The current is already flowing, so we are limited by those resistors in each location. So it doesn't matter whether we've got an ammeter before or after the resistors, we are going to get the same current at each of those locations. So we can say that we've got resistors in series here, and our current is in series. So we've got our current total is going to equal current 1 plus, equal to current 2, equal to current 3. And again, this is Kirchhoff's current law for series. Okay, and so we don't really need to solve, we do need to figure out a total resistance here so that we can figure out our total current, because our total current is going to equal each of these individual currents, but in order to find those, we are going to need to figure out a total resistance. So we've got resistors here. Are they in series or are they in parallel? Well, they're in series, so we're going to use our resistance law for series. Okay, this is for series. And so our resistance total is going to equal resistance 1, which is 4 ohms, plus our resistance 2, which is 3 ohms. We're going to get a total of 7 ohms resistance. And now we can put this into Ohm's law, and we can say, well, we're looking for the total current, which is going to equal our voltage total over our resistance total. We've got our voltage, or our potential difference there, of 14 volts. And we know our resistance is 7 ohms. So we've got 2 amps. Okay, and again, like we said, coming back up to this top equation here, that is going to be the same amperage at each of these points. So all of those things, we can say it simply IT equals I1 equals I2 equals I3, and they all equal 2 amps. So there's our answer for our first question. Okay, now let's have a look at what we've got next here. So this actually wasn't a combination circuit just yet. We were just employing Kirchhoff's laws. So here we've just got a series circuit. If we come down here, we've got just a simple parallel circuit. Okay, so it's asking us here, what are the values of R2 in this circuit? Okay, so why don't we just list what we know? So we know our voltage total is equal to 12 volts. We've got a current total is equal to 5 amps. And again, let's just make this clear. We could have had the ammeter on this side, it still would have read 5 amps, right? Because you go through the node, your current total splits, so let's call this our current total, splits into I1 and I2 at this junction, and then when they come back together at this node or junction, they're going to come back together, and so you're going to get I total back out on this side. So again, doesn't matter which side we're looking at in this case, they're both going to read 5 amps. All right, what else do we know here? We've got a resistance 1 is equal to 3 ohms. We've got a resistance 2, and that is the one that we're looking for. Okay, so what do we know? Well, we've got resistors here that are in parallel. So we can say, we could figure out if we wanted to figure out the total resistance of these things, we would say we've got a total resistance is equal to resistance 1 plus 1 over resistance 2. This is our parallel resistance law. Okay, so we can't figure this out just yet because we've got two unknowns here. We don't know our resistance 2 and we don't know our resistance total, but we said at the beginning what we would like to be able to do is figure out a total values. And what we do have totals for, we've got a total for voltage and we've got a total for current. So we can simply use our Ohm's law here. So we'll come back to this and we'll use Ohm's law. We'll say we are looking for resistance total, and that is going to equal our voltage total over our current total. And so we've got 12 volts over our 5 amps. And that's going to give us 2.4 ohms. So this is our resistance total. Well, that takes care of this unknown here. So now we can plug this into our resistance total equation, right? We can take this and plug it in here, and we can solve for our R2 unknown. So let's go ahead and do that. And we'll rearrange that equation. We'll say now we can take 1 over R2. That's going to equal 1 over our R total minus our 1 over R1. Okay, and 1 over R2 is going to equal, well, we could do it that way. We can also say this, remember. R2 is equal to 1 over RT, and sorry, we know what this is, 2.4 ohms, minus 1 over 3 ohms. And we could raise this all to the power -1. And now it looks like we've got a problem here because it looks like we're going to end up with a negative value, right? Well, no, we're not, because we've got 1 over 2.4 minus 1 over 3.0. So 1 over a small number is actually going to give us a bigger number minus a smaller number. So don't let that worry you. Keep going ahead, and you will find that your resistance 2 is equal to 12 ohms. And if we got sig figs, yep, sig figs check out there, looking for 2 sig figs. There's our answer. Okay, no problem so far. Not looking at combination circuits just yet. We've looked at a series circuit, we've looked at a parallel circuit, we've done our applications of Kirchhoff's law and used Ohm's law in there as well. So here we go. Let's get down to our first combination circuit. So when we look at this thing, it is asking us what is the potential difference supplied by the power source. So we are looking for voltage total here. Okay, so let's again write down what we know. Looking for voltage total. We've got a current total, and we know we've got a total current there because that's before we get to any junctions. So we've got a current total there of 8 amps. We've got a resistor 1 with 3 ohms. We've got a resistor 2 that has 3 ohms. Resistor 3 equals 3 ohms as well. Okay, so we've got everything we know here. So what is the first thing that we can do? Well, we can identify right here that we've got this parallel piece. And so we can say, if this is our first circuit, we know we can reduce this thing down because we can collapse these 2 resistors down to something simpler. So the way that we're going to do that is we're going to use our 1 over R, and we don't want to call this R total and confuse ourselves. So let's come up with a new notation for this thing. We'll call this the total of 2, 3. So we'll call it 1 over R2, 3 is equal to 1 over R2 plus 1 over R3, and we'll say R2, 3 is equal to 1 over 3 ohms plus 1 over 3 ohms, and we'll raise that all to the power of -1, and R23 will give us, let's see here, I've got it written down at 1.5 amps. Or sorry, 1.5 ohms. Okay, so here's our first important bit of information, and now we can simplify our circuit. We can draw our second circuit. There's our ammeter. We've got our resistor there, our resistor 2, 3 that we've just created here. Okay, and now we can say, hey, we've got our resistors in series, so why don't we go ahead and figure that one out? So we'll say, now we're using the series law, so again, let's call this final this one will be our resistance total when we figure this out. So let's use the RT notation, and we'll say it's resistance 1 plus resistance 2 to 3. So resistance 1 was 3 ohms plus 1.5 ohms gives us 4.5 ohms. All right, so now we've got the simplest circuit that we can have with a single resistor here. And what other information do we know? Well, if we're looking for our V total there, we've got our ammeter here, which said our current was 8 amps. And we've just said that this total resistance, and we can call this I total, our total resistance is 4.5 ohms. Okay, so now we can figure out what is our V total. So let's come over here and we'll say our V total is equal to our I total times our R total, which is 8 amps times our 4.5 4.5 ohms. And all together, we are going to get 36 volts. Okay, so again, this is our simplest combination circuit that we've got, and we can go, let's just make it clear. We've done two simplifications here, where we've used our parallel resistance law, and then we go into our series resistance law to give us our simplest circuit. That gives us our total resistance, and from our total resistance and our total current, we were able to figure out total voltage. All right, moving right along here, we're going to do example number 4, and this one is asking us, we're looking for a bit more information in this one. What are the values of V1, V2, and R2 in this circuit? And actually, again, this is not a combination circuit here that we're dealing with. We've got just a parallel circuit where we're looking for some different information, right? So again, let's start by writing down what we know. We've got a total voltage of 40 volts. We've got a current total equal to 10 amps. We're looking for that voltage 1. We're looking for voltage 2 as well. And we are also looking for the resistance in 2 there. But we are given resistance 1. Okay, so where are we going to start? Well, we want to be able to figure out, we said off the top that we'd like to figure out our total resistance, and we can actually do that right off the top here because we've got a total current and we've got a total voltage or a total potential difference here. So let's go ahead and figure out our resistance total, which is, if we turn our equation around, it's going to equal our voltage total, 40 volts, divided by our 10 amps. And we're going to get 4 ohms here. So this is important for us. Why is this important? Because we've already collapsed this now. So we've said essentially this would be what this circuit looks like. And let's just keep everything consistent with the way we've been doing it. Where we've got a 40 volt here. Our current is 10 amps. And we just figured out that our resistance total is 4 ohms. Okay, so from this simplest circuit, we can say, okay, well, let's go back up and figure out what's happening at each of these resistors. And we know from our Kirchhoff's law that if this is 4 ohms across here, and up here we've got resistors that are wired in parallel, that we're going to be using our resistance in parallel equation. Okay, so we've got that total resistance, and we are looking for R2 there. So let's rearrange ourselves here. Okay. So our R2 is going to equal 12 ohms. So if we know that our R2 is 12 ohms, Well, then we've got some information here that will allow us to figure out the voltage across each resistor. So if we've got a voltage total of 40 volts, then we know actually we can just use our voltage law here for resistors in parallel, or for a parallel circuit, and we can say that our voltage total here is going to need to equal our voltage 1, which is going to equal our voltage 2. And so we actually have our voltage 1 and our voltage 2 are going to be the same across each of these. So we've got, well, let's just write it up here, 40 volts, and we're looking for 2 sig figs. So our answers are for resistor 2, we've got 12 ohms, and for our voltages, so our voltage totals are going to be, our voltage total is going to be 40 volts, and our voltage at each of those resistors, or our voltage drop across each resistor, is going to be 40 volts. Okay, so relatively simple circuits so far. Now we're going to go on to things that are a little bit more difficult looking. Okay, so in this first one, this is a combination circuit, and let's just quickly go through and identify the different pieces that we've got here. So we've got a parallel section here, and we've got a parallel section right here. And so they've actually drawn the diagrams for us here and have said, well, what we could do is we could collapse these two resistors down into one resistor. So these two parallel resistors could become this resistor right here. And we could take these two resistors and have them become this resistor right here. And then once we've got that, we could say, well, now we've got all of our resistors in parallel, so we could just look at total resistance and turn all of those into a single resistor. Okay, so it's going to take a couple of steps to get there, but we already know how we're going to do it. We're going to take those parallel sections first, we're going to condense them into a single resistor each, we'll end up with a parallel. Our second circuit will have all of our, series resistors. So this will be our first, here's our second, and here's our third circuit. Okay, and the third circuit is our simplified version. That's as easy as it gets. So we want to know, what is the current flowing in the circuit diagram below? Okay, well, let's not write down all of our knowns and unknowns, but let's do one thing that could help us. Let's go around and label these. So we'll say that's R1, we'll call this guy R2, here's R3, R4, R5, and R6. Okay, so just for labeling, this is going to be R2, 3, and this is going to be R4, 5 when we get to it. So let's figure these things out. So we can say our resistance at R2, 3, what's going to become R2, 3, is equal to 1 over resistance 2 plus 1 over resistance 3. And we are going to have, so resistance at 2, 3 is going to equal 1 over 8 ohms plus 1 over 12 ohms. We're going to raise that all to -1, and we're going to find that resistance 2, 3 is equal to 4.8 ohms. Now we can do the same thing for resistor, what's going to become 4, 5 when we condense these things. Okay, so resistor 4, 5 is going to equal 1 over 20 ohms plus 1 over 30 ohms, all to the power -1, and our R4, 5 is going to become 12 ohms. Okay, so let's just highlight these. They're going to be important values for us, and they've got the values in there, so let's put these in. So 2, 3, 4.8 ohms, 4, 5, 12 ohms. Now we've got all of these things nicely in series, so we can go ahead, and I'm going to change up our color here. For our second circuit, we can use our resistance in series, and this is going to become our total resistance. So we've got resistance, and let's make sure we're calling these the right things. Resistor 1 plus resistor 2, 3 plus resistor 4, 5 plus resistor 6. Okay, so total resistance is going to equal 15 ohms plus 4.8 ohms plus 12 ohms plus 10 ohms. So our total resistance is going to get 41.8 ohms. Okay, and why did we go through all that work? Well, now we've got a resistance total, we've got a voltage total there, and we are being asked to find the total current flowing in the circuit diagram below. And I think they've given away the surprise for us there. So let's just go ahead and finish this off. So now we can do our current total is going to equal our voltage total over our resistance total, which is going to be 60 volts over our 41.8 ohms. That's going to give us 1.44 amps. Three significant figures for this one. Okay, 1.44 amps. All right. Again, I'm just going to do this one more so that you've got lots of experience walking through these things, and then I'm going to let you go ahead and try the rest of these on your own. But example 2 is asking us what is the potential difference across the 6 ohm resistor in the circuit shown. Okay, so we've got this section here where we can see that if we condense these series resistors into a single resistor, we would have these two resistors in parallel, which we could then put together, and that would give us a single resistor here. Then we would have these two in series. We could make a single resistor there, and we would get down to our most simplified circuit. So we're talking about making 1, 2, 3, 4 different circuits to get down to our most simplified circuit. And it's asking us for the potential difference across the 6 ohm resistor. So we are going series, parallel, series for our resistors. So our total is going to equal R1 plus, again, let's go through and label these. R1, R2, R3, R4, R5 here. So let's not call that R1. We're going to put R2, R3, and 4 together, and we won't call this our total. We'll call this our 2 to 4. And our 2 to 4 is going to equal 4 ohms plus 6 ohms plus 14 ohms. And so we're going to get our 2 to 4 equals 24 ohms. And they've given you the answers in here, so we've got a nice little check for ourselves. 24 ohms there, that's looking good. And now we can say, okay, we've got these things in parallel. So we can say these are going to become, well, we've got resistor 2 to 4 here, and so this is going to become resistor 2 to 5. Because we're going to have all of these resistors together. So we'll have this become resistor 2 to 5 in parallel. So we're going 1 over resistor 5 plus 1 over resistor 2 to 4. So resistor 2 to 5 equals 1 over 8 ohms plus 1 over 24 ohms raised to the power negative 1, and our 2 to 5 becomes 6 ohms. All right, good, so everything's checking out for us so far. We come down to our third circuit, and we'll make these clear. Getting a little bunched up here. So we're going to put these last two resistors together. So again, we've got a series arrangement now. So we're going to have resistor total is equal to resistor 1 plus resistor 2 to 5. So resistance total is going to equal 3 ohms plus 6 ohms, giving us 9 ohms total. Again, we've got a little check down there. They've already drawn it for us. So perfect. It looks like we're good in terms of total resistance. Now remember, they've shown us our total amps here at the bottom, but we didn't know that at the beginning. So if we had just been given the first diagram and were asked to figure out the resistance across the 6 ohm resistor there, we would have had to do all of these steps independently and draw these circuits ourselves. And so we would have come down and we would have found that we've got 9 ohms, and we would have said, well, our current is going to equal our total current is going to equal our total voltage over our resistance total, which is going to be 18 volts over our 9 ohms, and that would give us our 2 amps of current. All right, so now we've figured out our total current of 2 amps. So how is this useful to us? Well, we can start working our way backwards now. So with our 2 amps, we can say if we come back up to our third circuit, then our I total here is going to be the same as our current throughout the rest of this circuit, and that gives us some useful information, because if we know the current and we know the resistance here, we can figure out the voltage drop across that resistor, and that resistor is the one that we called 2 to 5. So we can figure out, let's figure out our voltage drop across resistor 2 to 5, and that is going to equal our current total times our resistance 2 to 5. So voltage 2 to 5 is going to equal those 2 amps times our 6 ohms, and gives us voltage 2 to 5 is going to equal 12 volts. Okay, so we've got that 12 volts, and how is that helpful? Well, if we know that it's a 12 volt drop across that resistor, then if we come up here, we know due to our parallel resistance rule, or a parallel voltage rule actually, that this has got to be 12 volt drop across each of those resistors. Okay, so how is that helpful for us? Well, now we can figure out our current through this portion of circuit 2. And so our current there, so we'll say this is when our current total splits into current 1 up here and current 2 down here. So we can say current 2 is going to equal our voltage through 2 to 4 divided by our resistance through 2 to 4, which is going to equal 12 volts over 24 ohms, going to give us 0.5 amps. Again, how does this help us? Well, now we can come through and we say we know that this is I2 through all of these, because these are all in series. So because of our current law, we know that these are all going to be I2. And now we know a current, and we know our resistance through our resistor 3 here. So we can finally come in and say, well, we can figure out our voltage drop across resistor 3 is going to equal our current 2 times our resistor 3. So voltage drop across resistor 3 there is going to be 0.5 amps multiplied by 6 ohms. And that is going to give us 3 volts. Oh, then let's do correct number of sig figs. Okay, so again, as we talked about in the instructions, it's all just breaking these down, combining series and parallel components so that you work yourself down into the simplest version of the circuit to figure out all of your totals, total voltage, total amperage, excuse me, and total resistance, and then working your way back up, keeping Kirchhoff's laws in mind for series and parallel circuits. Okay, so give yourself some practice, go through the other examples that we've got here, and we'll save this formative assessment for a little bit later. Okay, so just finish off the other examples here and practice those up, and then we'll revisit these next time in class.